Hey guys, in this video we're going to talk about an extremely important way to get rid of carboxylic acids, and that's called decarboxylation. So guys, decarboxylation is going to be a very important reaction for the rest of Orgo, so it's really important that you understand how to do it now. And the way that it works is that a beta-carbonyl carboxylic acid can decarboxylate in the presence of heat. Okay? And what this does is it produces CO2 gas as a byproduct. It evolves, okay, out of the material, okay? Now what a beta-carbonyl carboxylic acid is just that you have some kind of carbonyl beta to your carboxylic acid, okay? When you heat that up, what's going to wind up happening is that you literally cleave the entire carboxylic acid off and it becomes CO2 gas, leaving only the carbonyl portion behind. Okay? Obviously, we need to get to the mechanism for this because it doesn't really make sense just drawn like that. So let's do the mechanism. Now, guys, for this mechanism, it's going to make a lot more sense if you do one thing. Okay? If you rotate the bond. So we're going to rotate this bond up when I draw it because it's going to make a lot more sense with the mechanism. So I'm actually going to draw my OH facing like this and my carbonyl down. But this is still the same exact molecule, I just rotated it, okay? And you should too. So when I draw this mechanism, it's actually a series of 4 arrows, and there's no right place to start or no right place to end. It's all concerted, but I like to start from the oxygen grabbing the H, because that's kind of like an easy place to remember for me. So I would start with the O grabbing this H. Okay, so it's going to start off like that. Now, if I make a bond, I have to break a bond, because H can't have 2. So now this single bond is going to give its electrons and become a pi bond between that carbon and that O. Well, now that carbon has 4 bonds. Instead of breaking the bond to the carbonyl, though, I'm actually just going to break the single bond to the carbon completely. Notice what this is going to do is it's going to release my C with 2 O's on it, because now there's no single bond connecting it to the alkyl group, the alkyl group. Finally, once I make that bond, I have to break this bond. And there you go. Those are the 4 arrows. We wind up getting, this is a heat-mediated reaction, I wind up getting something that looks like this. R with an OH with a double bond. And I'm going to get CO2. Okay? So now it makes sense why I get the CO2 gas. Okay? And it should even make sense why the carboxylic acid's gone. What might be a little confusing for you is that I told you that you get a carbonyl from this, right? And right now I have an alcohol. That doesn't seem to make sense. But guys, this is something that we're going to talk about a lot more if you haven't talked about it yet. But there's something special about vinyl alcohols. Does anyone remember? What's special about vinyl alcohols? Guys, they undergo this completely separate, special process called tautomerization. Tautomerization. Okay? Now, if you want more information on tautomerization, I have an entire video for that, and there's an entire section of your textbook dedicated to tautomerization and enol chemistry. This is called an enol. Okay? Enol or enolate chemistry is a huge deal. So, you're going to get there if you haven't yet, okay? But the whole point being that when you tautomerize, what you do is you switch the locations of a double bond and a hydrogen. So what this actually becomes after tautomerization is this. This is the keto form, okay? So you wind up getting the ketone. Just take my word for it, that it tautomerizes, and then you're fine, okay? Awesome. So what I want you guys to do is for the next example, go ahead and predict what the product would look like. I know it's a big, complicated molecule. Predict it, and then I'll explain what's going on.